Hello, Math 157ers. We are going to do a presentation here on confidence intervals. And as part of that, I'm going to teach you how to use the confidence interval calculator that I created. So in here, we're going to just talk about M&Ms first. Have you ever tried to figure out how many M&Ms are per bag? They always tell you per weight, and you could probably get an approximation by, looking at a bag, opening bags. But the idea behind a confidence interval would be to take a whole bunch of samples of bags. Maybe you get those bags at checkout, and you could take 40 of those bags and count how many M&Ms are in each bag. And you could use that data to help you develop a confidence interval. So some basic facts about confidence intervals around the mean. We use a point estimate for a parameter. So here we're only talking about the mean, so we're going to use the sample mean as the best point estimate of the population mean. So when we construct a confidence interval estimate, we're determining an interval of numbers that are based on a certain probability that it contains the unknown parameter. So we don't say I'm 80% certain that this is the true population mean. We can say with an 80% level of confidence that the true population mean lies between this number and this number. Okay? So if you thought about it in terms of actual data sampling, if we took 100 bags of M&Ms, and we counted the number of M&Ms in each bag, and we constructed, based off that data, we constructed a confidence interval at a 90% level of confidence. 90 of those intervals that we would have constructed, or 90 times out of 100, an interval will contain the true population mean. These are 3 of the linked recordings for this section. So if you haven't watched them yet, I ask that you pause my recording and watch these 3. And they're noted in the recording lecture section. So let's get back to confidence intervals. Typically, students learn how to construct a confidence interval using Z first. But the important thing to know is that if you are using Z, the Z distribution here, you really do have to know the standard deviation of your population to be able to use it. Since if we knew the population standard deviation and the mean, we wouldn't even have to do statistics. It's just not really reasonable that this would happen. But we're going to use a new distribution that you just watched something about called the T distribution. And the thing to know is as our sample size gets bigger and this thing called the degrees of freedom in the T distribution gets bigger, it starts to look more and more like the Z distribution. So if we have a really big sample, let's say we have a sample size of 500, it's almost irrelevant if we're using a Z or a T distribution to calculate this. So we have learned about the Z distribution, and the student's T distribution is similar but different. The T distribution depends on the sample size. So it is symmetric, it's bell-shaped. The area in the tails, how skinny it is, how wide it is, that's going to really depend on the sample size. But again, just like the normal distribution or the Z, the area under the curve is 1. It's symmetric around the mean, which is 0, with half of the distribution on the left, half on the right. And as T increases, without bound, the tails will never equal 0, but they'll get much closer. And the area in the tails of the T is a little bit thicker than the area in the tails of a normal distribution. And that's because you were using our sample standard deviation as an estimate, which introduces more variability in the T distribution. But as one important property, again, as the sample size increases, that density curve gets closer to the standard normal density curve, also the z distribution. That it just occurs because as the sample size n increases, the value of the standard deviation of S will get closer to the actual value of the population standard deviation by the law of large numbers. So what does this look like? A confidence interval is a form x bar, the mean, plus or minus the t statistic, the t of alpha over 2, multiplied by the standard deviation divided by the square root of n. The margin of error is the part after the plus or minus sign. We talk about a lower bound and an upper bound. So the lower bound is your point estimate, your estimate for your population mean minus the margin of error. And your upper bound is your point estimate plus this margin of error. Degrees of freedom are defined as your sample size minus 1. Okay, so again, let's just look at a couple of confidence intervals. If you look at the 90% confidence interval, that means we are trying to make sure we encompass 90% of the data, whereas a 95% confidence interval, we're trying to encompass 95% of the data. So the width of a confidence interval is going to be bigger if we're using a 95% confidence interval versus using a 90% confidence interval. And these t of alpha over 2 values are coming from distribution in the area left in the tail. So numbers right where my mouse is going up and down would help us determine our test statistic, our t of alpha over 2. So I have a spreadsheet that we're going to look at in a few minutes, and there is a link in here to how to construct confidence intervals on the TI-84. So you can go back to the lecture notes and get that link. So let's talk about determining confidence interval. We have 22 textbook weight and find they have a mean weight of 39 ounces. So that's going to be our X bar. Assume the population standard deviation is 6.9 ounces. Based on this, we want to construct a 99% confidence interval for the true population mean of the textbook weight. So our N is 22, our X bar is 39, our S is 6.9, and we have everything that we need to calculate a confidence interval. So this is where I'm going to show you the beauty of the spreadsheet. So let's go to our statistical analysis spreadsheet. And when you come into it, it will usually end up on this one variable descriptive statistics. So we have to go over a bit. And this first one here, confidence intervals for the means, summary data. So we're going to enter in our mean, which was 39. Our standard deviation, our S, which is 6.9 ounces. Our sample size here was 22, and I think we wanted to go for a level of confidence of 99%. So we're going to enter 0.99. So let's look at this. Our margin of error was roughly 4.165. Our critical value of t, the software will calculate that for you, 2.8313. So this is your t of alpha over 2, which is dependent on your sample size. Your margin of error. So if I were to take 39 and subtract 4.165, I would get 34.835. And if I were to take this number and add it to 39, we're going to end up with this number down here. So you could write your confidence interval as your X bar, mean plus or minus your margin of error, which is this number, or you could take it as your 39 plus, or you could just write it in an interval form, parentheses, with 34.83, comma, 43.17. Close the comma. I do have a confidence interval calculator for the mean. Population standard deviation is known, or a big sample size. We're only going to use Z. And just to show you, let's say I had done this using Z, which is not correct for what we're doing. We get quite a different confidence interval. We go from 35.21 to 42.789. But again, remember when I said if you have a big sample size, it almost doesn't matter. So let's say instead of only taking 22 samples, we took 100 samples. Look how close our numbers are getting. 37.187 versus 37.22. And our critical value of Z is 2.57. Our critical value of T is 2.626. So they're getting really close. But let's say I increase that tenfold to 1,000. Look at these critical values. They're almost exactly the same. 2.57, 2.58. And let's just say I had 10,000. If I had 10,000 pieces of data, then we're getting right into where they're almost equivalent. But again, for this class, we are going to be using T for means. Also, you could figure out the minimum sample size you needed. So let's say I want to do a 90% confidence interval, and I want my margin of error to end up being 6.9. Oh, no, I need to decide on my margin of error. So I want my margin of error only to be 3. And my standard deviation was, again, 6.9. So my minimum sample size here was 15. It's pretty small. But what if say I wanted to do a 99% confidence interval? Then my sample size bumps up because I'm encompassing more of the data. Typically, we don't love sample sizes that are less than 30. That's just an old rule of thumb. Not a lot of rhyme or reason, but we don't love them that are less than 30. So let's go back to our presentation. So here, I wonder if I have this written down. How would I express this confidence interval 5.82854 in the form of x bar plus or minus the margin of error? Unfortunately, Google Presentations doesn't let me do that. So I need to find the midpoint of 582 and 854. So how do I find the midpoint? Well, I could add them together, 582 plus 854. And I'm going to take that total number and I'm going to divide it by 2. So I need to go up, I need to find a calculator. I don't see it right here. Well, it doesn't want to help me here. I know I have a calculator, but we're going to do this offline because it's not liking this. So I'm going to use my offline calculator I have over here. And I'm going to say 582 plus 854. And that gives me 1436. And I need to divide that by 2. So 718. So the midpoint of this confidence interval is 718. So it's really my x bar is equal to 718. So I would write this confidence interval as 718 and plus or minus the margin of error, which I don't know yet. But the margin of error is just the difference between the lower number in the midpoint and the higher number in the midpoint. So I've got 854 minus 718. Which is 136. And if, it's just as an exercise, if I took 718 minus 582, it is also 136. So I could express this as 718 plus or minus 136, which is the margin of error. We do have homework problems on this, and it's amazing that it's not difficult, but conceptually we still have a lot of trouble with it. All right, so let's go back to our presentation. It is just taking a long time today. All right. Two scientists want to know if a certain drug is effective against high blood pressure. So the first scientist wants to give it to 1,000 people with high blood pressure and see how many of them experience lower blood pressure levels. Or the second scientist wants to give the drug to 500 with high blood pressure and not give the drug to another 500. What's the better way to test this drug? What do you think? Well, if we gave off 1,000 the drug, we wouldn't have anything to compare it to, right? Like we wouldn't have a baseline. We wouldn't be able to see if this drug was effective. So we're going to go ahead and say 500 get the drug. Okay. Again, here's another example. We'd like to estimate the proportion of all Americans have good intuition about experimental design. How many people would answer 500 get the drug and 500 don't? So what's the parameter of interest here? How the percentage of Americans who know good experimental design. And what's the point estimate? Well, we'd have to take some data. Parameter of interest is all Americans who have good intuition about experimental design. And that is the population proportion. And our point estimate would be a proportion of sampled Americans who have good intuition about experimental design. And that would be our sample proportion, p hat. Dealing with proportions, sample proportions will be nearly normally distributive with the mean equal to the population mean, p, and the standard error equal to this equation, the square root of p times 1 minus p over n. But we have conditions that we have to satisfy. Each observation has to be independent of each other. And here, n times p and n times 1 minus p has to be at least 10. So we have to know that we're going to have at least 10 successes and 10 failures. When the population parameter, the population is going to be unknown, the p is going to be unknown, so we're going to use p hat. So what percent of all Americans have good intuition? So we'd have our, again, just like with means, we're talking about proportions here, we'll have our point estimate plus or minus our margin of error. So our point estimate is plus or minus our critical value times the standard error. How are we going to find these two things? Well, this is all over the place here. Our standard error, because we don't have the population proportion, is going to be p hat times 1 minus p hat over n. We're going to take the square root of the whole thing. And again, this is going to be our margin of error. So we're going to take our point estimate this is part of our margin of error, Point estimate is our critical value times this, we call this the standard error of the point estimate, SE. So what's left to find is our critical value. Although we just talked about how the t-distribution is used for means, we have to use the z-distribution for proportions. So for a 95% confidence interval, that critical value of z would be 1.96. So our confidence interval would be this p hat plus or minus 1.96 times our standard error. All right, so the GSS found that 571 out of 670, which is 85% of Americans, answered the question on experimental design correctly. So our n is equal to 670. Just looking at this, do I have at least 10 successes and 10 failures? Do I have at least 10 people that said yes? I do, because 571 is much bigger than 10. And my failures were people who got it wrong. Well, the difference between 571 and 670 is 99, so I have at least 10 failures. Okay, independence, the sample was random, and we're dealing with less than 10% of all Americans. Therefore, we can assume that the responses are independent. And our success failure, we take that 670, which is our total number, times 0.85, which gives us 571, and 670 times 0.15, which gives us 99, which are both greater than or equal to 10. All right, so how would we design this? Well, we're dealing with proportions. So our p-hat was 0.85, which we know. We told you before for a 95% confidence interval that it's 1.96 for our z estimate, our critical value of z. And then we have to look at the formula. It's the square root of p-hat times 1 minus p-hat, so that's 0.85 times 1 minus 0.85, which is 0.15, divided by n, divided by my total number of n. So that is going to be A. Now let's take a look at how we can do this on the spreadsheet. Let's see how we can use one of our tools to help us. Go back to our statistical analysis spreadsheet, and we're going to have to tab over. And we're going to tab to the one called CI and hypothesis testing for proportions. There's a lot going on here, but we only care about the top for now. In this case, our X, which is the number we got right, was 571. My sample size was 670. And I wanted to do a 95% confidence interval. And there's my proportion, 0.85, my standard error. Here's my margin of error. And there's my lower and my upper bound for my confidence interval. If I changed it to a 0.9, my confidence interval actually should get a little smaller. Let's take a look back. 0.95, my confidence interval is 0.825 to 0.879. If I only want to be 90% confident, it goes 0.8296, 0.8747. So again, the larger our confidence interval, the bigger our critical value will be, the more data under that curve we're going to be covering, and our confidence interval will be larger. Now let's just talk about, let's say you got a question and they told you that your n was 800, and they told you that your p, your proportion was 0.9. So your p equaled 0.9. The problem here is I don't have my x, right? Do I know what my x is? Well, I know my n is 800, and I know that I want my p-hat to be 0.9, so how do I find my x? Well, I would take 800 times 0.9, and I would find that my x was 720, and then I could do the problem. So I've got 720 over 800, and if you look right here, my p-hat is 0.9. So you can use this calculator even if you do not have, even if you're given the proportion and the sample size. Let's go back in here for a minute. 0.82, 0.88. So what if we wanted to cut the margin of error down? All right, well, here's the issue. We can start out with our margin of error, and we want that to be 0.01. Again, our z of alpha over 2 was 1.96. We have our square root of 0.85 times 0.15 divided by n. And the issue is we don't know what the n is. So we square both sides. We square 0.01. We square this whole thing, gets rid of the square root sign. We have 1.96 squared. And we're using that estimator that we used in the problem. And then we basically have to solve for n. And it gives us this calculation, 4898.04. But we always you can't have 0.04 of a sample. So your minimum sample size has to be 4899. You always just have to round up after, no matter what, to the next full number. So I did create a calculator for you on here. So let's see if we can get 4899. My level of confidence was 95%. Our P was 0.85, and we want our margin of error to be 0.01. And this is calculating us to be 4897.86. So this is going to give us 4898, which is okay. Let's go back, make sure we use all the same numbers. Which on a quiz or a homework, you would just simply have to tell me that you were off by a very tiny bit, and that is probably because this calculator is using more than 2 decimal places for its Z. But 4898, 4899 both would be perfectly fine as an answer. Let's look at the last slide. Now, final slide is if you aren't given a point estimate to start with, you want to start with 0.5, because that point, it's just as good as any, but if you think about it, when I multiply by 0.5 by 0.5, I get 0.25, and that's going to end up giving me the biggest possible sample size. And that's why we will use 0.5. So when you aren't given a previous estimate, you're going to use 0.5. Okay. So additionally, on this calculator, we're only concerned right now with the top part for proportions. We go back over. There's confidence intervals for the mean with the summary data, and it also has a minimum sample size calculator on here that you can use. And if you were given a problem where you were given data, let's say you're given some data, and I'm just making stuff up, and here's your data points. You can put your data in, you put your level of confidence in, and it's going to do a T calculation. So you can just change what's in the yellow, and it will give you a confidence interval. And because I put something so low on there, that's why it's such a large confidence interval. All right, well, thank you for watching, and I hope this was helpful. And please use the TI, use the spreadsheet. Don't try to do these calculations by hand. Thank you.